To the first session of this morning. It's my great pleasure to introduce the speaker, Professor Helge Holden from Norwegian University of Science and Technology. I think this is your first time to visit IMPA. Well, welcome. So today he will talk about, he gave a survey talk, okay, about the Camassa Holm equation.
Thank you very much. First of all, I would like to take an opportunity to thank Herman and Felipe for the very kind and generous invitation to come here and give this talk. As Gichan says, this is my first time in Rio, it's my first time in Brazil, it's my first time in Latin America, so I'm having a great time, as you can all imagine. When I started to prepare for this lecture, I honestly wanted to do a fairly extensive survey of the Camassa Holm, but I realized after a short while that there's too much material to do an honest survey of all the aspects. So I will focus and probably make a certain biased selection of topics. So I will focus on the Cauchy problem, which probably will fit this audience, or hopefully will fit this audience well. So I will start with 3 problems that I will eventually address throughout my lecture. So the first problem is that I will present a solution, an explicit solution of a nonlinear PDE. Probably you can guess what the PDE will be, but here is the solution. And at a certain time, the whole solution, u sub x, all derivatives, vanish identically for a certain time. You start with something non-zero, and you end up with something that is identically 0. And this is a homogeneous equation, so also 0 is a solution for this equation. So you have this problem that this has the Cauchy or the initial value problem will be problematic when suddenly out of non-zero solution you get something that is identically 0. So this will certainly pose some well-posedness questions that we will have to address. The second problem is of a completely different kind. So you consider the group of diffeomorphisms on the line, and you give yourself a right invariant metric, and you ask yourself, what are the geodesics? So we'll look at 3 different metrics. First is the usual L2 norm. The second is the L2 norm of the derivative. And the third one is a combination of the two, so the H1 norm. The third question, the third problem, is much simpler. So we look at an ODE, which is, of course, is a classical counterexample because the right-hand side is not Lipschitz around the origin, so you lose uniqueness of the standard existence uniqueness theory for ODEs. You can restore uniqueness if you impose the extra condition that it should be strictly increasing, the solution should be strictly increasing. Then you have uniqueness, and you have continuity with respect to data. But the question is, can you restore Lipschitz here? It's not Lipschitz in the Euclidean metric, but can you find a different metric that makes it Lipschitz? So the explicit solution in case of a strictly increasing requirement is given here. So V naught is the sine square root. So this is a nice solution. Depends continuously on the initial data. But it's not Lipschitz in the Euclidean norm. So if you take the difference between 2 solutions, you get the right-hand side there, which you can see is not Lipschitz here. But you can, and that will be the challenge, is to find another metric that makes it Lipschitz. So let's return to problem number 2. So we are on the diffeomorphisms on the line, and we want to look at metrics and determine the geodesics. So the first one is the L2, and most people will probably know the answer to this, which is a Burger's equation. We would then do compute the characteristics in the usual way. We now have a solution in Y, which depends on, is parameterized for each t, and it depends on psi. We have what I will call the Lagrangian velocity. And we can rewrite the system in terms of these variables. And you see out of this nonlinear PDE, we get a very nice linear system of all these that you can easily solve. So from the nonlinear Eulerian picture in Berger's equation, we can translate it into Lagrangian variables, and it turns out to be a very simple equation. So we start with a graph like this, and it's a function for each time. But eventually we know that the faster waves will overtake the slower waves, and we get the familiar solution of this type, which of course is no good as a function of x, but as a curve, this curve is as smooth as this curve. There's nothing wrong with this curve at all. So in the Lagrangian picture, everything is nice. So we have a parameterized curve for each time. We can even write down explicitly what it is. And it's a smooth, nice curve. Nothing wrong with it. Because the problem when we want to go back to the Eulerian picture, it's not that easy at all. And we can see this curve is equivalent to the implicit equation given x and t you want to solve for u. And this can only be done in the regimes where there is a simple solution here and here. So the idea is that you have an equation in the Eulerian picture, you go to Lagrange where everything is much simpler, but you are paying a big price when you want to go back. We also have another issue, the issue of relabeling. So there are many ways to parameterize this curve that give the same curve, and they will eventually give the same solution here, but there is a lack of uniqueness in the Lagrangian picture that has to be resolved. So it's hard to say something new about the Berger's equation, so we turn to the next metric, which is the L2 norm of the derivative. And here the answer is the Hunter-Saxton equation, which is another nonlinear PDE. There are many ways to write the right-hand side here. Quite more familiar is maybe when you take a derivative of the whole thing here. So you get the x derivative on top of this on the left-hand side. Then all the integrals disappear, and you get 1/2 ux squared. It's a common way to rewrite Hunter-Saxton. But once you integrate, there are many different forms that are not necessarily completely equivalent, because you have to decide where you start to integrate from. Again, you play the same game. You do the characteristics. So, and you rewrite the Hunter-Saxton in Lagrangian variables. You need to introduce, in addition to the velocity, the energy up to the characteristic here. And you can rewrite the equation, and you end up with this system, which is slightly bigger than for the Berger's equation, but it's still linear. So in the Lagrangian picture, this equation is quite simple to solve. But going back to the Eulerian variables, to the original u variables, is again very hard. One could talk easily for 45 minutes or an hour about the Hunter-Saxton equation and the way of going back, but I will not do that. That's a separate lecture. Let's go to the H1 norm then. And the answer is then the Camassa Holm equation, which is written here. It's a nasty one, and it's not exactly very pretty the way it's written here. And I guess no progress has been made on this equation when you start in this form. You always rewrite it in a different form. It is a strange equation because it has time derivatives sitting here and here, nonlinear convection, nonlinear diffusion, nonlinear dispersion, and these numbers and signs matter, in contrast to the KDV, where you have a lot of freedom, where you can scale the way you want essentially. You cannot do the same thing here. You change the equation. You do the same game, you do the characteristics, but here you get a nasty surprise. So here is the thing. H is as before, U is as before, but you get new quantities, Q and P. H is the integrated energy up to Y. But these Q and P are no longer so nice. They depend on U and H and Y and the derivatives. So the system is no longer linear. But still it turns out to be, and that we will return to this issue many times throughout the talk, to do it in the Lagrangian picture because of the possibility to construct a solution here. So if I take another derivative, this is the way, with respect to psi, this is the way that I'm going to look at it. It's a system, 3 unknowns, 3 equations, so in principle you can solve it. But it comes with constraints, because these y, u, and h are not independent because they come from this Eulerian picture. They have to satisfy this on top. So if you start with initial data for this and you just solve it, how can you know that this will be satisfied? So things are much more complicated. Let's go back to problem 1 now. With the information that we have now, we have computed the characteristics. So let's see what the picture looks like in terms of the characteristics. Here is a picture that I had with the characteristics. Makes it much more clear that the 2 peaks move together and they collide here. All the characteristics come together, but in contrast to the hyperbolic equation, they do not collide. They come out with the same tangent. And all the tangents here are vertical. And at the endpoint of all these characteristics, the value is 0. So everything is 0 at this point. So of course one possibility is to continue with 0. Nothing can prevent us from doing that. But you see this picture is so symmetric that it's very tempting to just reflect this and continue with something coming out that is non-zero. We'll also do that. So let's look at the energy to try to understand what happens when the solution itself vanishes identically. So this is a messy picture. If you start with 5 units before the collision, the energy is concentrated at the 2 peaks. If you move to the dotted line, we are 2 units away from collision. They move together. Here it's 1 unit away. They almost overlap. And at collision time, everything is concentrated at 1 point. And this is the energy like that. So it's quite convincing that the energy concentrated focuses at the origin in terms of a delta function. Point-wise, everything goes away. But if you look at this quantity, it looks very much delta-like. So a natural idea is then to extend the solution concept. So in addition to the Eulerian variable, u, we also add the energy. To allow for this delta, the way we do it is that we consider the energy as a radon measure, non-negative, with absolutely continuous part that satisfies this, which allows for a delta in addition. So beyond wave breaking, so we had the possibility to continue with 0. We also had the possibility to reflect. And of course, this is a natural way to reflect, to continue out with the peaks passing through and coming out on the other side. We'll return to this issue. So let's stop and do a little bit of background for the Camassa Holm. Here is how it was written down the first time. There is a kappa that wasn't present in my presentation so far. I presented as a initial value problem. And it was first studied in a fantastic paper by Camassa Holm, Fils-Revelet in 1993, where they give all the fundamental properties of the equation. It's just an incredible paper. There are not many mathematical, rigorous results, but they have the key elements of the equation. It was derived as a model for water waves. So you take the Green-Nagdi, you take Euler, you take in gravity waves, so you look in the shallow water approximation, you have 2 small parameters, and then enforce a certain relationship between the 2 small parameters, and you expand, and you see whatever is left. It's a very delicate expansion to do, and in fact there are some questions about whether this is entirely correct derivation that is in this paper. But it's even more impressive that they ended up with somehow the right answer if they made a small mistake in the calculation. But there are now many derivations of the model. But it is very subtle. I don't think you can expect this to find this in your bathtub with a shallow water approximation, whatever careful you are with the initial data. It's a very subtle thing. But it was derived in the context of water waves, but we have seen from my second problem that you can also derive it in a geometric context, which in some sense is much more robust and also allows for extension to higher dimension. It is, and that was explained in Camassa Holm paper, is completely integrable. You have a lax pair. However, the lax pair is infinitely more complicated than the corresponding lax pair for the KdV equation. It's much more delicate to analyze the linear part here. You can also do, and I've done that to a large extent and to a large degree, to study what is called algebra geometric solutions. So you set up and you can build up a hierarchy of an infinite hierarchy of equations, of which Camassa Holm is the simplest. And then you can study what is called algebra geometric solutions that corresponds to a hyperelliptic surface and solutions of a very special kind that you can write down explicitly. That could also be a separate talk, but it's not going to be the one I present today. It also has soliton-like solutions, and we have seen two of them colliding. And I should say that this kappa, we'll return to that as well. Kappa is the depth of the water in the shallow water, so you shouldn't really put it equal to 0. However, most people do it because there are some advantages with it mathematically. And these soliton solutions, these multi-picons, only exist for kappa equal to 0. I mean, there are not known explicit solutions of this type where kappa is non-zero. It has bi-Hamiltonian, it even has infinitely many Hamiltonians, bi-variational, and it has wave breaking, as we have seen, in the sense the derivative goes to infinity as t goes to some finite time, while the H1 norm remains finite. Infinitely many conserved quantities. So the first kind of results, and this area was pushed a lot by Adrian Constantine and New Commercial. Adrian Constantine made his PhD at Courant with Henry McKean as an advisor, and the topic was the Camassa Holm equation. So he has studied this for many years. And a classical result is this one. So you start with initial data in H1, which is the natural space, and you look at this quantity. If you remember well, this is the guy that you take the time derivative of in the Camassa Holm equation. If this is non-negative, then it has a unique global weak solution. So the key quantity is this m. If you destroy this non-negativity of m, things go bad. So if u is odd with this constraint and it is in H3, all of these combined implies that this is no longer has a definite sign, then there is a finite time before the solution, before you have wave breaking. Most of these results that I call first generation results, these results, are done with the Kato method and analysis of that kind. And they rewrite the equation, and this is a way to more easily remember it. But there are other ways to write it, and I will return to that. And you see this u minus uxx is the guy where you take the time derivative. So it's not so surprising that this plays a special role. So I will do kappa equal to 0. I'll return to what the differences will be. But we have studied also kappa non-zero. So this is the way we rewrite it. This is our favorite way of rewriting it, and you can see if you want to rewrite it in this way, also the numbers and signs in the original equation matter. You cannot expect to rewrite it in this way. So it looks like a burgers with a pressure here, and the pressure is governed by some additional equation, and because you can integrate here, doesn't help you much at this point, but that's the way you can look at it. So here's what I want to say about the kappa. So if u solves the one with a kappa, then v of this form will solve it without kappa. So you see that if you want u to be an h1 function, then v will not be. So it changes everything. So if you want to study the problem with kappa non-zero, and you want to have an h1 function, then not much help is going to be given by this. And indeed, the Picon solution that we will see will not exist if kappa is non-zero. So we have studied also the case with kappa different from 0, but I just want to say that there is a difference, and it's a technical difference, but it has to be overcome. In the periodic case, it doesn't matter. If you want to rewrite Hunter-Saxton and find it difficult to remember, you can just use this, but with a slightly different definition of P. You throw out this term and this term, and then you have a Hunter-Saxton. So let's look at the P-con. This is a solution of the equation. This is a P-con solution. And it goes like this, but you can see that it's not really a regular solution because it's spiked here. So you have to rewrite the equation as in a weak form before you can interpret this. It also has many of them, multi-P-cons, that can be written as this. It's a sum of single P-cons, but the speed is no longer constant, the amplitude is no longer constant. A beautiful fact is that the P and Q are given by this set of ODEs. And you see, it really matters the sign of the Qs, whether they approach each other or the way they move in the same direction. You can even write it as a Hamiltonian system like this. It's a Hamiltonian. It's a very nice system. But as an ODE, it has this devious sign function, which is not exactly very continuous. So here is two P-cons. And like with the solid on KDV, the big ones go faster than the slow one. And it overtake or exchange mass. You can use the words you want when they move like this. It's more interesting when you take two of them colliding. So this you have seen before, and now you know what it is. They annihilate each other. They are identical mass in the two, and they just evaporate at this particular time. So the question is how to proceed. And there are many options, but there are two more prominent options. One is to remain zero, which is called the dissipative solution. And one is to pass through, and that's the conservative solution. And we'll study both of them. So conservative solution, we have seen that the derivative goes to infinity, and the energy goes to a delta. And one can derive formally a conservation law for the energy that is satisfied this equation. So here is the conservative one, 0, and then it comes out. So how to proceed beyond wave breaking? That was a difficult topic for a long time. And it wasn't really understood before Bressan and Constantine reformulated the Camassa Holm as an ODE, taking values in a Banach space. And we will follow, however, a different kind of rewriting that I did with Xavier Renaud. It's a different system and that gives more details in the structure of the solution. And the key, as we have seen, U is not enough. We have to augment it with another variable. And we are going to show this. And Bressan, with his student Fonte, also derived a transport metric. We will go beyond that and show Lipschitz metric eventually today. So here are the system here's a system that we want to analyze. And as I said, it's a closed system, so you can in principle solve it. But there are these extra constraints, and you have to make sure that they are preserved. So you cannot really take any initial data and solve and hope that will make your day. You have to be very careful. So we are looking at these are the unknowns. If you haven't seen this data before, it's because it hasn't been here before. It's just for technical reasons we subtract this from the y. So this is a set where we look for initial data and also the solution. So we insist that these guys should be non-negative, these guys should be non-negative. However, they can become zero because that is a key issue. They will become zero. That's when we have wave breaking, when this becomes zero. But they will not be zero simultaneously, which is very important. So the sum will always be positive. We have this additional constraint. So if we enforce this initially, we will have this for all t. That's a result that is not obvious, but it's true. So that will give us and I jump some arguments here that will give us a unique global solution in G. From Lagrange to Euler, which is a tricky thing, and I will be brief here. We have this and we go back. So the question is, can we find an x here that corresponds to this? Fortunately, it is so that in the case where we can, this will give a unique, well-defined function. To give the measure, we simply get it from the y. So we use the push forward like this, and we get the measure. So I will now try to illustrate. I've tried a couple of times to do more details in the explanation. It's not always that successful, so I will use more graphic aids to show it. So we are in the Eulerian picture here. We have our initial data and the initial measure. We translate this into the Lagrangian picture. So I use capital X for the Lagrangian variables. And now I have to come up with y, u, and h, but I don't have any solution to construct the y from, so the characteristics. So I have to do a different method. So here's how I do it. I construct y of xi in this way. I have the measure, and that's all I have essentially. I do the h and I do the u. So this is my initial data out here. Then I solve it like this. So x of t is the semigroup coming from the initial data. And hopefully I can go back to my Eulerian data. The problem is the relabeling that we saw in the Burgers equation. There are many candidates, in fact, there's a whole set here that correspond to the same Eulerian, and I can do the same thing here. I can go back. And the question is, can I really go back, or do I end up a completely different place? Fortunately, it so happens when we are careful in setting up the initial data that indeed this is invariant. So this is a relabeling. If I relabel the initial data, that's the same as taking the unlabeled, unrelabeled, and then relabel afterwards. We tried to make insist on a certain cut here, and select this and use that as our selected element here. But the solution doesn't want to follow this, so this didn't really turn out to be a good idea. So it's still to find a metric here in this space that is Lipschitz, and that's what we eventually want, is not easy. So the semigroup that we get in this way is continuous, but it's not Lipschitz. So let's return to this simple problem of OD, and this is used for illustration only. I mean, I'm not claiming that if you understand this, you understand the Camassa Holm, but it's just to show that, try to illustrate this on a simple example. So we want to determine a Lipschitz metric. Here's a solution which is clearly not Lipschitz in the Euclidean norm. So by looking at the equation, it's not difficult to come up with this metric that divides by the square root here. And in this metric, the distance between two solutions is unchanged. It's conserved when t evolves. So this is a metric that will make it Lipschitz. It's not Euclidean, but I will show how to derive this in a Riemannian context. So if you look at the Euclidean metric, the distance between 2 points like this, we can consider this as the infimum of all paths connecting x0 and x0 bar with all smooth paths connecting the two. That would be the infimum. But it's, as I said many times now, it's not Lipschitz, the solution with respect to this metric. So if we study a little bit more the equation, we can take another time derivative here with the dot. We see that the equation has this form. which we can rewrite using the equation as this one. But this is a clue to construct a Riemannian manifold. So we consider real line as a Riemannian manifold. Where at any point x, the Riemannian norm for any tangent vector v in the tangent space x is given by this quantity. Because this quantity is a well-defined definition. And if we now define this metric as the infimum of all paths connecting the 2 points given by this, and we constrain ourselves to path with a definite sign, so they are not going back, but they are going in increasing direction. If we rewrite this, we will get exactly this metric by change of variables. So this is a way to derive this in a more natural setting, in a Riemannian setting, that we will try to mimic, and we have mimicked in the, for the more complicated equation Camassa Holm. So, and here, and this was not well appreciated by our referees of a couple of papers that we wrote on this, that there is a big difference between the periodic case and the full line case. So we did the periodic case because that's often simpler. So with this, is a very natural metric to define the distance between 2 points in the Lagrangian setting. So you take these as the relabeling, and you just take the infimum of the distance here. And this satisfies this invariance with respect to labeling, which is something we really need. However, it does not satisfy the triangle inequality, so we do not have a metric yet. But I will show you a trick to get around that. But this definition, even if it's a very natural thing, it's the first thing you come up with, works for the periodic case. It does not work in the full line case. It's a little bit too technical to go into the reason why it's not, but it doesn't, and this is something that works. Again, we take the different relabeling here. We take this combination, we take the minimum.
What is B?
B is just a short name for the Banach space that I'm looking at all of these quantities in. It's a combination of L2, H1, one space for each of the variables. But this simply is what we need in the full line. But to use either this or that to get a metric that satisfies the triangle inequality is a nice trick here. You take a finite collection of points going from your left point to your right point, x alpha to x beta, finite collection of your points, and you do the infimum of this quantity here. And that will give us a metric that satisfies the triangle inequality, and which is invariant on the equivalence classes. So this gives us our theorem that if we have initial data that consists of the measure and the U, and U is in H1, mu is a radon measure with this property. There exists a continuous semigroup that gives a weak, conservative, and global solution of the Camassa Holm equation. And this semigroup is Lipschitz continuous on sets of bounded energy. So indeed, we can measure the distance between these two at a certain point, and they are bounded by what the distance is initially. How do we know that we actually have a conservative solution? Well, we can see that the measure is conservative or satisfy this conservation law. So it's interesting to compare this metric with the more common one. So if you have convergence in H1, this implies that in this metric you have convergence of the corresponding measure here. And if you have convergence in this measure, it implies convergence in L infinity and weak star convergence of the measure. So it's somehow in between these two norms. But it's certainly not Lipschitz in either of the two norms, so you need something in between. So here is a nice 4 pecan that goes through, and you can see it's also nice to see the characteristic, and it's a matter of linguistics whether you will say that the negative pecan, antipecan goes through like this, or whether it's reflected off like that, like the characteristics seem to indicate. So let's look at the dissipative solutions. They are much harder mathematically, because in the conservative you just want to keep everything that's there. It drops away for a short time, but it comes back if you're just careful. But with the dissipative, it's gonna disappear. So again, this was done independently of Bressan and Constantine, and work with Xavier Renaud. So we rewrite. Again, we use the same trick in Lagrangian variables. And we rewrite the system like this. But now we have to make sure that we select the dissipative solution. So, and this is indicated by when the characteristic disappears. So we take the biggest time for which this guy is positive all the way from 0. If this is infinity, then nothing really happens, and we can conservative and dissipative, and everything is the same. If this guy is finite, we are at the point where we have to decide whether we are conservative or dissipative. The way to do it is that we want to be dissipative, we insist that this guy should remain constant for all t bigger than tau. And this is then the system we have to solve. And this is a harder system because of this characteristic function that creates discontinuities for the ODEs. So this is messy, but I want to explain what the key part of how to resolve this. So one can solve both show both in the dissipative and conservative case that there is a certain inequality between these concepts or these quantities here. So it's a higher dimensional space where I project it down, where we only see y sub psi and u sub psi. So we are confined between these two circles. Now, if we are here, we are attracted, the solution will attract us to the origin. That's the way the dynamics of this system will go. You are attracted to the origin if you are close here. At the origin, you have two choices. You can pass through, then you're the conservative guy. You can remain stuck at the origin, then you're the dissipative guy. That's when, because then you should remain 0 for the derivative, you should remain 0 here. Or you can pass through. But the dynamics will push you through. So you have to, the problem is that if you compare a point just above the horizontal axis and just below the horizontal axis, these points are close when you look at the conservative solution, they're very close. But in the dissipative, very far apart. There's no relationship between something that's a little bit above and a little bit below when you talk about dissipative solution. They are far apart. And this picture doesn't really show that. So we have to introduce a function that moves the upper part away from the origin. Because there are many choices here to be made. Not all of them will work. In fact, very few of them will work. In fact, we only found one that will work. So we take a function that has this form. We are actually in a high dimensional space, so it doesn't really matter exactly what the function is here. And we measure the distance between 2 points here using this function. That will separate the origin, split it up. Then we can introduce a norm like that. And it's a theorem that this norm will satisfy this estimate. So here is the theorem that we eventually end up with. Now we only need initial data in H1. There is no need for a measure here. One has a continuous semigroup describing a global weak dissipative solution. And to make it different from the conservative, we can show that it satisfies this kind of entropy condition, that the derivative is bounded by this quantity here. So it decays like that. And that is certainly not satisfied for the conservative solution. We are working on the Lipschitz metric here, but this is much more complicated. There's one technical stumble block left. So I will, as a side issue, look at the pecons. They can be used also for numerical purposes. So you approximate your initial data by multi-pecons. And then you can approximate as well as you want in H1, and you can use them because they can be solved explicitly. And they will work nicely also in cases where you have no clue about what the solution will be. And with Renault, we extended this to the dissipative case. That will give us the dissipative solution by using the dissipative multi-pecons. So there has been many generalizations of the Camassa Holm equation. People were very excited about it because all of these fantastic properties. So there have been many generalizations, some to a more spatial dimension. As with KDB, it's not so easy to go from one dimension to multi-dimension as a model for water waves. In the geometric context, one can do it, but it hasn't really been studied that much. But system generalizations, there are many of them. In fact, it's hard to know whether they are all different or there are some magical transformations that will yield them identical. And the most popular one is the following one, which so you take this one, that is the good old Camassa Holm, and you just add this equation that looks very familiar to people doing fluid dynamics. And the relationship between the P and the other quantities, the rho and the U, is given by this. So you just add this factor. This has also been derived in the context of water waves, so it has a physical setting. It was first written down by Oliver Rosenau in 96, so very short after Camassa Holm was written down in 93. But they derived it in a completely different context, in a geometric context, where they were playing around with equations with certain properties. So it was only much more recently that it was realized that this could be analyzed with and was related to all the theory that had been developed for Camassa Holm. And the question we asked ourselves, of course, was, will this Lagrangian picture that we developed carry over to this system? To me, it was very much tied to this equation with exactly this form, and it was not given much freedom for, or much hope to extend this beyond the Camassa Holm. However, and this looks, completely different. However, it turns out that it does, in fact, apply. So if you introduce Lagrangian density, which is rho times y sub xi, it will satisfy this relation, and in addition, what we had before, which was a conserved our relationship between the quantities, is now just amended with this r squared. But we get one important consequence of this, namely, if r starts by being positive, then this guy will never vanish, so no singularities will develop. So we don't get the dichotomy between conservative and dissipative solution. No singularities, just be one solution. So this equation regularizes the other equation. So the theorem that we derived on this, and I decided to, as an example of how you can do this with very different asymptotics at plus and minus infinity, so that to show what the theorem then will look like, is I did it for this example. So I take this function, which is an h1 function, but I then add different asymptotics at minus infinity and plus infinity. Chi is just a function that is 0 for negative arguments, it's 1 for arguments above 1, and it's increasing function. It goes 0 up to 1. So this gives us the asymptotic value here at minus infinity and this at plus infinity. The density is a L2 function plus some constant. It's the same in both ends. Then one can show, and we have shown that there exists a global weak conservative solution of this system where the measures satisfy this conservation law. Now there is a regularity property of the system that is quite interesting, that you don't have for the Camassa Holm equation itself. So I'll just spend a few minutes on this. So if you have u, rho, and the measure, we say that it's p regular at an interval if u satisfy this, rho satisfy this, and the measure is absolutely continuous on this interval. So there are no deltas hidden there. Then the theorem says that if we start initially with a density that is non-zero on an interval, then the solution, and the initial data are p regular, then the solution will remain p regular on the interval determined by the characteristics. There will be no nasty things going on within this interval, and it will remain p regular. And this is certainly not true if you remove the rho. So here are some solutions. You can see whether we have a picon antipicon on top in the U, and there is a concentration of energy or rho at the origin when these points collide. So the natural question is to ask, so what happens if rho goes to 0? Will we then approach the solution of the Camassa Holm? So let's try to look at this in the where we make rho much smaller. So now it's 1 part in 10, so it's much more peaked here, and there's much more going on with the rho variable. But one can show that the conservative solution of the Camassa Holm equation is a unique limit of the solution when you take the initial density of the two Camassa Holm system to 0. So this, because of the regularizing effect, is able to select the conservative, not the dissipative solution of the Camassa Holm. So this gives a completely different way of defining conservative solutions of the Camassa Holm. So we are approaching the end here. So this is the equation that we spend 45 minutes on. This is the way to, I think this is the easiest way to write it if you want to remember it. The original form is hard to remember. And it has these nice properties that we have seen. So you can derive this in a geometric context or for water waves, especially if you are very careful with this. The best way, I think, is to translate the whole equation into Lagrangian variables and solve this system of these. And you have to resolve the non-uniqueness, the relabeling issue, which is intrinsic in the Lagrangian formulation. There's no way around it. It sits there. Then you transform back to Eulerian variables. And you have to include the energy if you want to study conservative solutions. Introduce a new distance, and this will yield a unique, weak, and global solution of the Camassa Holm equation. And we have a Lipschitz metric in the conservative case. And that's it. Thank you.